Hi pre-calculus honors, these are notes 4.1. Go ahead and pause the video and read the objectives for this lesson. So as you can tell, we're going to be talking about angles and a little bit of history. The idea of dividing a circle into 360 equal pieces dates back to the 60-based counting system of the Sumerians. The appeal was that 60 is evenly divisible by so many numbers. But today we're going to talk about radians. Here's your definition. A central angle has a measure of 1 radian if it intercepts an arc with the same length as the radius. So this might sound confusing, but radians make it possible to relate a linear measure and an angular measure because a radian is related to the radius of the circle. It might be a little bit more obvious if we take a look at an applet from GeoGebra. So this particular circle has a radius of 1. So as I change the angle in standard position, so now we have an angle that is 1 radian, and notice that the radius of the circle cuts an arc on the circumference of the circle of length 1 radian, which is the radius of the circle. So let's erase that, and let's go ahead and make that angle larger. So now we have an angle that is 2 radians. So we have the radius of the circle. Notice there are 2, so we're cutting an arc of length 2 radians, so 2 radius of the circle, right, on that circumference. Let's make it larger. Again, I like how this is color-coded for you. So now we have an angle that is 3 radians, so 3 radians. So again, a radian is just a radius of a circle. That's all it is. So now we have 4 radians, 5 radians, and let's see, try to get around there, 6 radians. Was anyone shocked that it was, a little bit 6.28 radians all the way around the circle? So again, that's 2 pi. So if I change the radius of the circle, now the radius of the circle is 2. The radius of the circle, oh, sorry, the apple can't get any bigger than 2. But notice that it is still, if you count 1, let's count them. 1, 2, 3, 4, 5, 6, and it looks like about 0.3, so approximately 6.28 radians, which is 2 pi. And so there you go. And so a radian is just a radius. So just to make sure we understand what's going on, if we want to sketch an angle of 4 radians in standard position, you start at the positive x-axis, and let's see, this is our radius right here. Oh, I did a terrible circle. So we know that 2 pi is all the way around the circle. So let's see, so 3.14 pi would be right over here, halfway around the circle. So this would be approximately 4 radians, because we have pi radians. This is 2 pi radians, 3 pi over 2 radians, and pi over 2 radians. Okay, so let's take a look at the next example. It says, find the length of an arc intercepted by central angle of 1/2 radian in a circle of radius 5 inches. So let's draw a picture. And the radius is 5 inches. So go ahead and see if you can draw a picture to describe the situation. Okay, so for number 2, a central angle of 1 radian intercepts an arc length of 1 radius, which is 5 inches. Therefore, a central angle of 1/2 radian intercepts an arc length of 1/2 radius, which is 2.5 inches. Okay, for number 3, it says find the radian measure of a central angle theta that intercepts an arc of length s and a circle of radius r. Go ahead and draw a picture and see if you could think of an example for number 3. Okay, for number 3, theta would have to be s divided by r, or arc length divided by the radius of the circle, because, for example, if you have an arc length that, in a circle of radius 10, if you had an arc length that was 40 inches, if the radius is 10 inches, so your angle theta would be 40 divided by 10, or 4 radians. So now we need to think about our next example. We know that 2 pi radians is 360 degrees, so to convert radians to degrees, we would multiply by 180 over pi. To convert degrees to radians, we would multiply by pi over 180. So go ahead and try for A, B, and C. Convert from radians to degrees and degrees to radians. Pause the video and give it a try. 7 pi over 5 is an angle in radians. So I multiplied by 180 over pi to convert to degree measure. And B was a 210 degree angle. We multiplied by pi over 180 to get an angle in radian measure. And 5, part C, that was 5 radians. It doesn't have a degree symbol. That is 5 radians. So you multiply by 180 over pi to get an angle in to convert. And we have an angle in degree measure now. The next thing we need to talk about is degree, minutes, and seconds. So if you would like to change an angle from degree, minutes, and seconds to a decimal measure, we know that there are 60 minutes in 1 degree and 60 seconds in 1 minute. So the first thing you would have to do is grab your calculator. We're going to change 58 seconds to minutes. All right, so 58 divided by 60, so there are approximately 0.97. 58 seconds is approximately probably 0.97 minutes. So let's add 14. So now we know that we have 132 degrees and 14.97 minutes. And let's divide by 60 to change minutes to degrees. So we have 132.25. That would be the angle in a decimal measure. 132.25 degrees. Okay, so now we need to talk a little bit more about arc length. So if we want to find arc length, remember we did this up here. We talked about how theta is S over R. So S equals R times theta. But that was when we're talking about radians. So a theta is an angle in radians. If you wanted to find arc length with an angle in degrees, you would have to first change that angle to radians. So let's do an example. All right. Okay, so for some reason the picture didn't show up, so I just drew it there for you. The running lanes are 1 meter wide, and the inside radius of lane, oh, that's supposed to say of lane 1 is 33 meters, and the inside radius of lane 2 is 34 meters. How much, oh my goodness, how much longer is lane 2 than lane 1 around 1 turn? Okay, so go ahead and pause the video and think about central angles. Okay, so each lane is half of a circle with central angle pi, because halfway around the circle is pi radians. So we know that the length, S equals R times theta, would be pi R. So the radius of the inside for lane 1 is 33 pi, and lane 2 would be 34 pi. So the difference is pi. So the person that is in lane 2 is actually running 3.14 meters longer than lane 1. Okay, so the next thing we're going to talk about is angular and linear motion. So we're going to go ahead and take a look at another applet for angular and linear motion. Okay, so from this GeoGebra, you can see that points on a radius of concentric circles, notice that those points have, here I'll stop it for a second, so these points have the same angular speed. Okay, so I circled the points in blue, so notice those points have the same angular speed as the angle is rotating around the circle. However, think about a linear speed. So think about, for example, if a person was running, the person on the outer circle, their linear speed must be faster, because think about how much farther they would have to go, right? That circle is larger. So the inner circle and the outer circle, their angular speed is the same, but their linear speed is definitely not the same. Okay, take a look at this little simulation here. So I'm going to look at, I'm going to press graph, and I want you to look at the red and the blue points. There we go. So I'm going to do this again. I want you to think, would you say that the red and the blue points have the same linear velocity or the same angular velocity? Okay, ready? Here we go. Okay, so hopefully you said angular velocity. Okay, so I'm going to go back and show you another example. Let's see. Oh, I'll take a look at the graph. So would you say same linear or same angular? All right, we'll watch it one more time. And again, you don't need to know about these equations. We haven't learned any of this yet. I'm just showing you a simulation with the angular and linear speed. So take a look. So again, would you say same angular or same linear? I think this might be a little bit trickier to see. Baseball's in there, so there's a point. Now let's try it again. So looking at the black and the pink point, would they have the same angular or same linear? Okay, so those actually had the same linear speed. Okay, so I might ask you, what types of units would you expect to describe an angular velocity? You might see radians per second. You might use revolutions per minute. Now for a linear speed, a linear velocity, you might see feet per second, or centimeters per minute, or miles per hour. So a lot of times the units make it a little bit easier. So if I asked you, will a point on the Earth's equator have a faster angular velocity than a point near the North Pole as the Earth rotates on its axis? And you would say, no. Right? The angular velocity would be the same. Okay, so we're going to do problem number 8. Go ahead and pause the video, read number 8, see if you can get started. Okay, so we have a child's bike, and the wheels are 12 inches in diameter, so that would be a 6-inch radius. So we're starting, it's a 50 revolution per minute, so that would be an angular speed, and we would like to change to miles per hour. So we're going to think about some units. Notice we have a revolution, and we know that 1 revolution is 2 pi radians. Now here's where some people get stuck. I might say, well, what is a radian? Well, isn't a radian just a radius? So the radius of this circle is 6 inches. Now there are 12 inches in 1 foot and 5,280 feet in 1 mile. So let's see, we had the revolutions cancel the 1. Oh, look at that minutes. So we need 60 minutes in 1 hour. So let's see, the minutes canceled to 1, and we have miles, the feet canceled to 1. So notice that if you multiply 50 times 2 pi times 6 divided by 12 divided by 5,280 and multiply by 60, you will get 1.78 miles per hour. So we just changed an angular speed into a linear speed. Okay, let's take a look at the next example. Go ahead and pause the video and give it a try. Alright, so she's traveling at a speed of 24 feet per second, and our goal this time was revolutions per minute. That was our goal. The radius of the wheel was 10 inches, so now we know that 1 radian is 10 inches, and I'm guessing that if people have trouble, this is the step they have trouble with, because again, what is a radian? It's a radius, and the radius of this circle is 10 inches. Do be careful when you use your calculator that you put parentheses around the 2 pi, or you do divide by 2, hit enter, and then divide by pi and hit enter again. Alright, let's try another example. Okay, so let's look at the pulleys. So notice that the smaller circle, notice that that circle has the smaller pulley has the higher angular velocity, and the larger pulley has the smaller angular velocity. However, if you look at the linear velocity, right, these two pulleys are connected. So the linear velocity for the outer edge of both of the two wheels is the same. It has to be, or the belt would break. See, I could change that, maybe make it a little bit more obvious. I think it helps with the circles there. So again, notice how that smaller circle is, the angular velocity is much faster than the smaller circle. But again, since these two pulleys are connected by a belt, their linear velocities on the outer edge of the circle must be the same. All right. So hopefully that helped. Go ahead and read problem number 55. Pause the video and give it a try. Try A, B, and C. Right? The angular velocity of the larger wheel is 120 revolutions per minute, so we change that to radians per second. Now for part B, it says, what is the linear speed of the belt? Well, we have 4 pi radians per second is the angular speed. So go ahead and pause the video and change to linear speed. So the angular speed was 4 pi radians per second. And we know that 1 radian in the larger wheel is 7 centimeters. So you could say 7 centimeters is 1 radian. So that means that the linear speed is 28 pi centimeters per second. However, the linear speed for the large circle and the smaller circle, they're the same because the circles are connected. So now for part C, if I said what is the angular speed of the smaller wheel, well, I know the linear speed. So I could find the angular speed considering the smaller circle, and the smaller circle, 1 radian is 4 centimeters. So 7 pi radians per second is the angular speed of the smaller wheel. Okay, so for the last part of the lesson, we're going to talk about bearing. Bearing is the angle of the line of travel measured clockwise from due north. So for example, if I had a bearing of 225 degrees, I would say north clockwise 225 degrees. That would be an example of approximately 225 degrees. If you look at a compass, it might also help to think, well, that would be southwest. Let's look at number 10. Go ahead and pause the video and see if you could draw a picture to describe number 10. Realize that A and B are 30 miles on an east-west line. All right, so notice it says the fire is a bearing of 78 degrees from A. So I drew a line north from A and I went clockwise 78 degrees. Now 300 degrees bearing from B. So for B, I would have to go 300 degrees. And notice the fire would be right around there, and this reference angle would be 60 degrees because, again, the bearing was 300 degrees from north clockwise. Okay, for number 11, it says the Coast Guard sends out 2 boats. Boat A is at a bearing of 300 degrees, and boat B is at a bearing of 290. So here's your harbor. If you go 300 degrees, that angle would be 60. There's boat A. And 290 degrees, I'll get a different color. That would be right about here. Notice the angle in between them then would have to be 10. We need to find arc length because we want to find out how far away the boats are from each other. And we know that arc length, S, is R times theta. So we need to first of all change 10 degrees to radians. Because when we use our formula S equals R theta, that angle is in radians. So that's a pi over 18 radian measure. So S is R times theta, and the radius, they told us, was the boats were 30 miles from the harbor. Multiply by theta, so you end up with approximately 5.24 miles apart. Okay, so for the last one, I want you to think about an angle of 135 degrees in standard position, and then consider a bearing of 135 degrees and what that would look like on a compass. Sorry about that. I think I confused you. I didn't want you to think of, I mean, you could if you want, but I didn't want you to think of a bearing of 135. I wanted you to think of what would the bearing be if it maybe had that same terminal side. So do you see how a bearing would have to be a bearing would have to be 315 degrees to have that same terminal side. And if you think about the compass, that would be northwest. Great job, everybody.